So we talked about FM and MFM encoding, and specifically and mainly because of my love for old hardware. Worth noting that there are many other ways of storing data as ones and zeros and transmitting them in a way that kind of prevents the kind of physics problems that we were talking about and the synchronization problems we talked about with, clapping and syncopation and all that kind of stuff. We did talk about serial transmission as well. So as well as us talking about how the floppy disk worked and the spinning thing, we talked about, in fact, our demo when I was clapping for you was a way of me serially transmitting 1 byte to you, which we completely failed to do, and as did most people in the comments from reading them, which kind of proves the point, I suppose.
It does, but when I look back at, I obviously looked at the edit and I could see the waveform, and I was like, it's so obvious looking at the waveform.
How funny.
I'm really unsure as to how I got it so wrong.
Right, when you're literally looking at the little peaks of the clap in the waveform view, which is, of course, exactly what the computer's doing as well. So you actually were able to see what the computer would do to see these peaks. Right, cool. So one thing I cheated with last time is I said to you, assume the first bit is going to be a 1 so that you knew when I was starting. When you connect two computers together using a serial cable, if you remember those things, or a null modem cable, or indeed, if you were using dial-up internet in the 80s and 90s on aughts, you connected to your modem through a serial cable. The transmission that used was similar to what we did actually by clapping. It was just literally the ones and zeros in the right place. Now, if you remember, you have these baud ratings like 19,200 and all that kind of nonsense. That's basically saying how fast is the clock going to be, and both sides just have to agree on that. You remember there was a little drop down in your program, and you just had to set what that was. There was also usually another thing in brackets that says something like 8N1. Something like that. It was like, 9600 brackets 8N1. And that 8N1 tells the transmitter and receiver how they're going to frame each byte, how they're going to say where the byte begins and where the byte ends. So all of these protocols have one bit that's always a 1 at the start. So it's not part of the data, but that first clap, you could imagine, is the thing that says, okay, I'm starting to send you something, so you start listening. Then you both set your metronomes going at the 19,200 that you've both previously agreed, and then there's claps or no claps, and then there's one stop bit. That's what the 1 is of the 8. 8 bits of data, N we'll get to in a second, and then 1 is the 1 stop bit, and sometimes there were 2 or whatever, but almost every modem I ever used was 8N1, which is to say 8 bits of data, 1 start bit, which is implied, and then 1 stop bit at the end. So that kind of gives you a way of saying, I guarantee that there's going to be 1 at the beginning and 1 at the end. And so even if I'm transmitting all zeros to you, I'm going to clap once, there's going to be a long old pause, and I'm going to clap again. And we hope that the speeds that we're dealing with at like 19,200 or whatever, are slow enough that our clocks can be in sync for that short amount of time. Seems reasonable, right? So let's talk now about how we might speed that up even more and transmit faster, for example, an Ethernet cable. So most of you, nowadays everyone's on Wi-Fi, which kind of ruins this slightly, but we're going to talk about 3 families of Ethernet speeds today. In the first one, we're going to have to introduce a new type of encoding of our ones and zeros, which on its face doesn't look much better or different from FM and MFM, but it has certain characteristics. So that is Manchester encoding. Oh. Yeah, so it was developed in the University of Manchester, and it was first used for storing data on hard disks. And it's very similar to FM and MFM in certain ways. So we're going to have 8 bits here. Give me a binary number with some ones and zeros, and maybe a few ones in a row and some few zeros in a row.
All right, let's go 111.
Yep.
00 100.
Worst episode of Countdown ever, right? All right, okay. Like before, we're going to use 2 bits or 2 clock phases to transmit each of these bits. That was similar to how we did with MFM and FM. And the 1 is going to be a 0 followed by a 1. So we're going to do 0, 1 for each of these, 0, 1. And then a 0 is a 1 and then a 0. And I'm writing the zeros and ones. Really, they're transitions of a clock pulse going up or down. But from our point of view, I'm trying to keep everything sort of mostly in the binary and computer domain, as opposed to the electronics that are actually going on behind the scenes. So we can always detect a clock, which is one of the things that we wanted to always make sure we had the beat of this. The beat is always coming. There's going to be at least one of these transitions every single bit. So that gives something like a clock circuit, something to lock onto and kind of get the tempo. So we're good on that front. And then it's pretty straightforward to see if the voltage was low when the beat came in. We're going to assume the beat comes in sort of in the middle of each of these. Then when it goes high, we know that we're transmitting a 1. And if it drops to a 0, we know it's a 0. So that's pretty straightforward. It's just what they chose to use for both these hard disks in the University of Manchester and then later on in some signaling applications. The problem with this is that we have sort of doubled the number of bits that we're sending. So we've kind of got 100% overhead in this way of transmitting data. We can do better than this 100% overhead. That was also true of FM and MFM. If you remember, MFM kind of just moved things around so we could kind of speed it up and not have to worry about the physics as much, but it was still twice as many bits of data. So this was used in 1 megabit Ethernet and also 10 megabit. And then there was something different that was used in 100 megabit Ethernet. It's related to what I'm about to talk about, and I don't actually have any direct experience of 100 megabit Ethernet. I have experience of 1 gigabit Ethernet, which was a big change. What 1 gigabit does is it takes our 8 bits that we have and it expands it to 10 bits. And now these are 10 real bits, so we've kind of got 2 more bits than we have to begin with. Now, if we had 8 bits, how many possible combinations of ones and zeros are there in 8 bits?
Is that 256, 255?
It is.
256, 256.
256 different combinations of ones and zeros. Now, what we want to do is we want to make sure that our bit that we're transmitting, these bits that we're transmitting, has a few important properties. One of them is that we need some ones to make sure that we've got something to keep the beat with. If it was all zeros all the time, you imagine if this was zeros, then we're back to the problem that we had right at the beginning where you can't tell where the beats begin and end. So we need a few bits in there. So let's just say we never want to have more than 3 or 4 zeros in a row before we think, well, actually we'll lose track of where the beat is. And then there's a couple of other interesting things that we'll talk about in a second. But what we could do is within this 10 bits, which is how many possible combinations of ones and zeros are there in 10 bits? I'm making you
1024?
You can do it.
I'm doubling and doubling again.
Yes,
right.
You're doubling it twice, exactly. So there are 1024 possible bit patterns. And so what we could do is we say, like, maybe we can find 256 of those 1024 that do actually have enough ones and zeros and gaps between them. And then we essentially make a mapping between the 256 possible things we'd like to send and 256 of these 1024 bit patterns. And the way that it's actually done is more complicated than I'm going to do here. It actually breaks it into 5 bits and then 3 bits, and then has different tables to look up and say, hey, well, these 3 bits look like this. But what I'd like to do is actually kind of work through the 3-bit case to sort of show you how the table was built. So this is if we wanted to transmit 3 bits, and we never want to say transmit 3 zeros in a row because that would be too long. So we've got all these possible combinations. So this is our 3 bits in, and then we want our 4 bits out. Like I say, the 8 bits going into 10 bits is kind of the 3 bits going to 4 bits, and then also a 5 bits going to 6 bits, and you kind of blonk them together, and now you've got your 10 bits, right? So 0, 0, 0, well, that already is sort of broken by our rules. Even if we could have 3 zeros in a row, there's no guarantee that the next one isn't also 3 zeros, in which case then we've got 6 zeros in a row. So our 0, 0, 0, we're going to transmit as 0, 1, 0, 0. We've just sort of stuffed a 1 in there, and now we're good. 0, 0, 1, on the other hand, we're going to say is 1, 0, 0, 1. And you could imagine filling out the rest of this table just saying that there are enough ones and zeros so that you never have the problem of, if you carefully look, the 0, 0 here, if we had 0, 0, 0 followed by 0, 0, 1, then we'd have 0, 0, and then there would be a 1 here. And so you kind of have to look at all the combinations of pairs as well to make sure that there aren't too many zeros coming at once. So rather than me boringly writing this whole table out here, you can imagine that that's what's going to happen here. So we have these 4 bits that encode these 3 bits. And now we're golden, right? We can transmit 3 bits and the 5 bits, get our code map together, and then to transmit, we effectively just look up in a table this 256 value, which 10-bit value should I send? And on the receiving end, you look at the 10 bits and you do the reverse. You kind of look up in a table as well, which is great. Okay. Except there are some other problems now. So one of the other issues that comes when you're actually transmitting data over these like cables is that Physics is involved again. Stupid physics, I know. In our lovely massless, frictionless world of ones and zeros, it's fab. But effectively, there's an amplifier at the far end that's trying to pick up on this signal, and this signal's coming through, and it has to kind of tune the amp so that it can clearly distinguish between the 1 level of voltage and the 0 level of voltage to pick a 1 or a 0. The way that it does this is it's like the automatic gain control in cameras, or the white balance, that kind of thing. So what it kind of does is it just sort of averages out the signal, and then it kind of tweaks it so that the average value is sort of halfway between 0 and 1. So you can imagine if you have 5 volts for 1 and 0 volts for 0, then it looks at it, sort of smears it out over a period of time, and it tries to make that smeared out value 2.5 volts, and therefore you're just as likely to get 0 as a 1, and that gives you the detector the chance of noticing zeros versus ones. That's cool if the average that you're sending is in fact halfway between. So you could imagine if, just in this particular example here, let's imagine the whole thing's 3B, 4B. If we were just sending streams of zeros, then we just get 0, 1, 0, 0. That's fab. We've got enough pulses to synchronize our clock, but on average, we've only got 25% of the full amount. So what we want to do is also transmit as many zeros as ones. So we need to tweak our table. And rather than me drawing it out again, I'll just sort of explain through where it's going. When we have 4B, we obviously have 16 possible values on this side. And so what we can do is we can actually pick several bit patterns that then match to the same output value. And as long as we pick things like, for example, what if we were to say, let's say the alternate version of this, let's just flip all the bits. Let's say another way of encoding 000 is to go 1011. Now, we'd have to make sure that wasn't also used somewhere else in the table, which it isn't in this particular instance. But now we can pick between 0100, which gives us 1 1 and 3 zeros, or 3 1s and 1 0. And so if we just keep track of how many zeros we've sent and how many ones we've sent, when we come to send the next code, we can pick the one that produces the difference between them, and so therefore keep this sort of average that's called DC balance at the halfway point. So that's another thing that we have to do. Now our 8B 10B over here, it is built out of those primitives. Out of the 1024 possible bit patterns, there are at least several ways of encoding most of the 256 values. Some of them are already balanced. Some of these 256 things are already 4 1s and 4 zeros, so you don't have to do anything with it. That gives us another useful thing, which is that some of those codes are valid by our definition that says, we haven't got too many zeros in a row, and they have an equal number of ones and zeros, but they don't map to any of those 256 bytes. So what we can use that for is for signaling on the wire to say something like, hey, I'm starting to send. And so there's a special bit pattern that says I'm beginning to send a packet, a piece of information. Then there's a bunch of data that is just bytes that will be encoded in the normal way. Then there's a pattern, a symbol that says, hey, that's the end of the message. And so that's how the other end knows that a single piece of data has been sent and received. The cool thing about all of this, of course, is that this has 2 bits of overhead for 8 bits of data. So that's a 25% overhead compared to, back in this world, a 100% overhead. So we're doing a lot better. So this is great. There are some other things that happen in this. There are other bit patterns that are transmitted. When there's no other data to transmit, it's transmitting certain bit patterns that lets both sides know that there is a receiver and a transmitter at each end, and they can synchronize their clocks. And some of those bit patterns, some of these 10-bit patterns are unique. They won't occur anywhere else in the data, and so that can be used to sort of lock onto the signal and know that you're decoding it right. And if you remember that if you've ever plugged an Ethernet cable in, there's a little green LED, right? Yeah. When you click it in, the light comes on. That light says that the hardware has synchronized on both ends and is detecting this valid pattern, and so it's always transmitting something. It's just this in between pattern. Right, we've got one last thing to talk about, if we haven't already made this the longest one ever, and that is, let's go to 10 gigabits fast Ethernet, even faster Ethernet. The overhead of 25% is just too great. So we don't want to keep doing this. It's just too much. What we want to do instead is pick a bigger chunk of data, not just 8 bits. Bytes are so passé. Let's pick 64 bits. Let's just draw it like a big slot here. There's 64 bits in here. I could do the same trick we did before and say, well, let's send, say, 66 bits, and then we have a table that lets us look up between 64 and 66, right? Except that 2 to the power of 64 is an astronomically large number. My table would get too big. Now, I'm sure we could build it out of smaller pieces like we did with the 8B, 10B with, 5 and 6 and whatever, but each one of those adds one more bit to it. I don't really have many options here, so I can't use the same table-based approach and this careful design of all possible combinations and permutations. So in a moment that absolutely blew my mind when I first worked out or learned how this was working, the way that we're going to do our 64 to 66 is we're going to send 2 bits at the beginning, which is either 0, 1 or 1, 0. The 64 bits that come after, we're going to, and I'm going to use little bunny air quotes, encrypt the data. If you look at encrypted data, it would look like what to you if you didn't have the key?
Oh, garbage, yeah.
Complete random garbage, right? So imagine we were transmitting encrypted data, right? It would all be random. And the thing about random data is that it's just as likely to be a 0 bit as a 1 bit. Yeah, we've got our DC balance now. Suddenly we don't have to worry about it now. But the other thing is that we don't want too many zeros in a row. How many zeros are there in a row in a random number? Well, it could be 64 of them. Now, we actually know that eventually after we've done 64 zeros, there is going to be a transition in one of these 2 bits we've shoved at the beginning. But it's incredibly unlikely that we're going to get 64 bits of zeros in a row. It's a bit like, I know that you've done hyperlog log, the sort of probability of getting these strings of zeros in a row is relatively low. So we're kind of getting a probabilistic way of saying it's unlikely we're going to have clock problems because there'll be enough ones and zeros. The DC offset averages to halfway, which is great. So this is a great way of doing it. Now we've just got the one problem. How do we agree on a key? Well, it's not really encryption. What we've got is, I'm going to draw a few of these, ... So I'm trying to remember 58, 57, 56. These are bits in a chain. Apologies if this isn't the exact right number, but we're going to have our bit that comes in here, and then we've got an exclusive OR, and we also have bit 0, I think, comes into this as well. I've drawn a very bad linear feedback shift register, which is a terrible way of making random numbers these days, but it's random enough. But if we use the linear feedback shift register and we put the bit one at a time through the system and exclusive OR it, we get effectively the bit exclusive ORed with this random number generator. Okay, so far so good. Now we've got random bits. On the other end, we feed those bits in as they come off the wire without decrypting them. There are 58 of these bits that kind of follow from one bit into the next in a shift register. So it doesn't matter. The first 58 times we do this, we are going to get junk. We don't know. But after 58 times, we've both agreed on what data has got into our feedback register. And so from now onwards, we will both agree on the decoded data. So it's a clever way of synchronizing this random number generator between the sender and the receiver without them having to agree on anything to begin with, right? You just have to accept that the first 58 bits is junk, and then after that you start seeing decoded data. And so we've been able to achieve our DC balance. We don't have to have massive lookup tables. It's actually really simple to develop these in hardware. Really simple. I mean, it's as simple as hardware is. And we've got the properties that we wanted, which is to say that we know that there's going to be enough transitions for our clock recovery to work. The DC balance is good. And we can transmit with only 2 bits of overhead for 64, which is about a 3% overhead. So that's pretty impressive. So all these encoding strategies are used in Ethernet. It's worth saying that the faster Ethernets, in terms of the copper cable ones that you're probably used to using, they actually use something cleverer using multiple pairs. There are 4 twisted pairs inside the cable. But some of the more, if you're using fiber optic cable, for example, which is still Ethernet, that will use these kinds of encodings. And if you're using radio transmitter versions of Ethernet, that is also uses these encodings. And that's where I have my own experience with this, where I've had to debug. And the reason I know so much about 8B, 10B is that if you have a radio transmitter, you get a lot more bit errors than you do on your average Ethernet cable. And so if a flock of birds, I don't know, flies through the line of sight, maybe you get some corruptions and then you have to spend ages debugging why everything went wrong, which was my life a few years back. So that's good fun. But no, the fact that this uses random numbers has just blew my mind, and is a great way of doing achieving the goals of what we need for these transmissions. It's worth also saying this is not just Ethernet. Things like the PCI bus inside your modern PC uses this to communicate. Things like SATA for, again, serial ATA. The serial is using encodings like this. What else? There's another one I found the other day. Oh, RFID tags apparently use this. So that's neat. Various different types of this thing. So anytime you need to transmit data, you're going to be using one of these kind of tricks for doing so.
Our channel sponsor Jane Street is always on the lookout for curious and talented people to join their teams across the globe. Maybe someone just like you. Now, Jane Street's a world-class quantitative trading firm. In addition to amazing jobs and internships, you can see they also run a variety of educational programs for pre-university and university students. There's a wide range of them, and they cater to people from all sorts of backgrounds. Applications for some are open right now as I record this. They differ in length and locations, but Jane Street will cover your costs. You could find yourself in New York, Hong Kong, or London, learning all about the latest in machine learning, programmable hardware, mathematics, statistics, insights that could be your first step into the world of global trading. Check out the Jane Street website via the links I've put down below in all the usual places. No finance experience is necessary, just a curious mind and a passion for problem solving.